All right, let's continue and put the final piece in for the first workshop on Python. And in this workshop, we're going to be dealing with more with arrays and then operations associated with matrices and vectors. We're going to illustrate some of that, and then as we move into the next workshop with typical chemical engineering calculations, you will get to see and you'll get to review how all of these operations are put into place. So let's go back and review how we can take a list type and then convert it into a NumPy array type. So I'm going to come up here and just define a list with our brackets that we always use. And I'll do a 1.5 and then a 3.2 and then a minus 6.4 and finally a 0.9. So that is a list. And if I just run this statement, it shows it as a typed list with 4 items, all right, or elements. And now what we're going to do is we're going to bring in NumPy module with our typical abbreviation, and then we'll create a NumPy array with the array command and put list1 in as the argument. And then let's run that code now. And we see that this is in alphabetical order, but the content, it looks the same, but this is an array of 64-bit floating point numbers, and its size is noted as 4, but it's noted as 4 with a comma, indicating that we could have multiple dimensions here. All right, so that's what we have. And then if I just include a simple print statement and we print this out, it shows down here the array, all right, and that is no longer a list, but now it's a numerical array, all right? So let's do a second example here after this one. We'll call it list 2, and we'll create another list using double brackets here, and then we'll do 2, 3, outside that bracket, comma, another set of brackets, 6, 1. All right. So we'll have that, and now if I run that, it shows list 2, but it's a typed list, and it says its size is 2 because it contains each one of these elements, all right, which in turn contain 2. And then we'll use our typical notation of capitals for multi-dimensional arrays or matrices, and we'll again convert this list into an array A. And here you'll notice that it shows it now as a 2-dimensional array. And here it has called it integer type, 32-bit integer type, because I did not include any decimal points. I think maybe if I go back and put a decimal point in one of those elements, it now changes everything over to float 64. And now it shows the size as 2 by 2. All right, so there's that one. And then just to illustrate a third one here, I'm going to, instead of having a list, I'm going to have a tuple, which is with our parentheses, and then I'm going to put in multiple elements here in brackets. Like so. And let's see how that shows up here. And it shows it as a tuple with 4 elements, and there are elements. But now I'm going to convert that into an array. And I suppose I might have called that something like tuple 1 because it's not really a list, but I didn't do that yet. So let's come down and see what we've got now for B. And you'll notice it's an array of integers, and let me double click this, and we can see that it is a column of numbers. And so it sort of correlates to a column vector, whereas the one up here was more like a row vector, all right? And then the one in the middle here looks more like a 2x2 matrix to us. So having those examples, let's pop over to our slide. And that just reviews this with the results. And these commands are available in this file name, convert list to array. And then just comments here that in Python terminology, the dimensions of an array are called axes. And A, in this particular case, has a single axis. B, capital A has 2 axes, sort of like row and column axes. And B actually has 4 axes, each one containing only 1 element, all right? So we're sort of looking at it that way in terminology that Python uses, okay? So let's come back to our editor and deal with another example here showing some functions that we use commonly to create arrays. And the first one we have to start again with needing NumPy here. And we'll create an array cap A as np dot zeros to parentheses 3, 2. Now let me clear out my variables over here so we can see more clearly what's going on. Let me try to run that. And what it's showing me here is that it's given me a 2-dimensional array or matrix with 3 rows, 2 columns, all filled with zeros, okay? So that we use quite frequently, that function to create empty matrices or vectors. And another example of that would be, and there's an important difference to note here, A is equal to np dot zeros, and let's just put in 5. And we'll run that. And we see that A is a 1-dimensional array with 5 zeros. And the thing to note here is that we only used a single set of parentheses and not 2 when we're doing a 2-dimensional array. So keep that in mind. And then there's a likewise function called ones. This is similar to MATLAB. And I'm going to put in 5, 1, which we generally interpret as being 5 rows and 1 column. And because I'm using the 2 arguments, if I only used 5, then it would just present a 1-dimensional array as a row. So if we do this, this creates this B array, which is a column of 5 elements filled with ones, all right? And then I can do another one here. Cap B is equal to NP ones, something like 2, 3. And we can take a look at what that looks like. And we see that it's 2 rows, 3 columns, and it's filled with ones, all right? So that is just a couple of functions that come in handy as we're putting together solutions to problems. Let's go back to our slides and look at that. This duplicates pretty much what I did, except it's showing with print statements what it looks like in the console when you display the items. And you'll notice here, excuse me, you'll notice that it creates these as floating point entries, all right, by default, okay? So we've got that. Now, I want to go back and we'll try another one here. And that is, we'll do C is equal to NPI, EYE, and we'll just put 4 in, all right? And then let's run that code. And I'll open up C here, and you can see that it's an identity matrix, 4 by 4. And the I is phonetically like the capital letter I, which we take to mean identity matrix in most of our matrix operations. So that's the I function, all right? And I think we have a simple slide that illustrates that for you and shows how the results are displayed in the console if we use a print statement, okay? So that's a little bit about simple arrays and some functions that we use with it. So we're going to start now doing some operations with arrays to illustrate the typical things that we may need to do. So let's come back and let's start a new file here for illustrating this, and put my usual NumPy import here. And then I'm going to create 2 arrays that are the same size, all right? Multi-dimensional arrays. The first is A, np.array, with double brackets, 3.6 and 2.1 for the first row, and minus 1.4 and 0.7 for the second one. And again, when we're doing multiple dimensions, note the use of an extra set of brackets, all right, inside the parentheses. And then we'll do another one for B, which will be the same size, but a little bit different in terms of the numbers. Minus 12 and 7.7. Come outside there, put in the comma. Another set of brackets, 2.1 and minus 1.9. And I do need my extra bracket there. Otherwise, it won't be happy. Okay, so at that point in time, I could do something like print A comma B. Could I do that? See how it's displayed and run that. And it's a little bit untidy because it starts the second one on this line here. So if I want to force a line, an extra line, I can put in a \n here and do it that way, I think. And now it shows my two-dimensional arrays, all right, that I have created. And now we're going to see how we can put these two together. So I'm going to create an array C, and I'm going to use the vStack function, which is vertical stack, two sets of parentheses, A, comma, B. And then let's just print C here, like so. And for the moment, let me just suppress this original printout by commenting it out with the number sign. So let's run this guy. And what we see is it creates a C array by stacking A on top of B, all right? So now the result is actually a 4x2 over here, and that is a vertical stack. And as you might expect and guess, there is an H stack, A and B, and we can print D. Let me just put in a line feed ahead of that, like so. And let's run that. And you can see that what he did is it stacked the B array to the right of the A array. So that's a horizontal stack, all right? And then we can do corresponding reverse actions by saying, for instance, arrays A1 and B1 are equal to NP V split of C into two equal-sized arrays. And then if we just do a print A2, B1, let me go back and fix that, it's A1. And go ahead and run that one. What we see down here is it gives us back our original arrays, all right, after vertically splitting the VStack. And then similarly, I can do an A2, B2 is equal to NP dot H split of D into two equal size arrays. And then, let me just do a shortcut here. I don't know if this saves time or not, but let me copy and paste that down here. Change the 2 1s to 2s. Let me comment this out so we don't see its output. And let's run that. And we see the same thing. In other words, it took the horizontal stack that we had up here, and it broke it down into two equal size arrays. All right. Now, these are a little bit limited in the fact that the splits split them into equal size arrays. We can always later on carry out splits by using specific ranges of indices, and we'll probably show that somewhere along the road eventually. So let's pop back over. This again shows the vertical stack and the horizontal stack, and that code's available in the file noted, although I typed it in. And then we've got the splits, corresponding splits, and we make the comment that you can do unequal size splitting, but you have to do that with a little more programming. All right, so we're now going to talk about reshaping arrays for a couple minutes here, and we'll illustrate that. So let's start a new file here. And we'll create an A array. Two-dimensional, 3.6, 2.1, 6, comma, 2.1. And the second one, in its own brackets, minus 1.4, comma, 0.7. Of course, you can use any numbers you want in there. So we've got that. And then what we're going to do is we're going to create an array lowercase a by using a Python method, not something that is in NumPy, which is a.flatten. And what we're doing here is we're saying that essentially A has two axes, and we're flattening it into a single axis. So, you know, we can see what that kind of thing produces. Let me get rid of these over here. And let's run this. And you can see that it gives 3621 minus 14.7. So it essentially takes it straight across and collapses it into an array of a single axis or a one-dimensional array. All right. So that's your flatten method. And then there is another one that's a little more obscure that is tricky. It's not the same, but we can come in here and we can say B is equal to Ravel, and this is again Python, a dot Ravel with empty parentheses. All right. And then if I print B, all right, let me comment this guy out up here. If I print B, it shows the same thing, but there's a difference here. And I'm going to illustrate that by coming in and saying I'm going to take the 2 element of B and I'm going to set it equal to 99. And then pretty obviously, if I print B again, it should show that change, right? Whoops. There's this and thing that it sneaked in on me, so let me get rid of that. And you'll notice it's the same, except it changed the third element. Remember the indices 0, 1, and 2. 2 is the third element to 99. But what's interesting here with this particular method is shown by printing the A array after we do that. And what we notice is that by setting an element of the B array, we have also gone back through and set the corresponding element of the A two-dimensional array. And here the difference is that essentially B and A correspond to storing the same numbers in the same memory locations, but it's just a different way of looking at it. And that's called a view, all right? So that's how that function, how that method is different from the flatten method. So it's a little bit of tricky, but let's go back and look at the slides here. And here it shows the flatten, all right? And it does not change what A was, but it in cap A, but in lowercase a, it flattens it into. Now, in this case, if I would go back and change an element of lowercase a, it would not affect capital A. So, you know, that, but with the Ravel method, you'll notice that it did do that. And that is a distinction that you might see if you look at some other code in Python. It's important to understand the distinction. We don't use this method down here very often in engineering and scientific calculations, but it's good to be aware of it, okay? And then the final thing, then, we do run into this from time to time, is we'll go to a new example, is reshaping an array, all right, reshaping it. And so we'll create an array cap B, and I'll put in 1, 3, and 5, and then I will have comma and a second array, which will be 2, 4, and 6, all right? Like so. If I clean this up and we run this, we get what we would expect, all right? First row, 1, 3, 5, second row, 2, 4, 6, okay? But now what we're going to do is we're going to create a different array, which is going to be b.reshape. Again, this is not NumPy, but it's inherent to Python, 3, 2. All right. And then we'll print D to see what it looks like. Got that right. So let's run that. And what you'll notice here is if we go back and look at B, 1, 2, 3, 4, 1, 3, 5, 2, 4, 6. Now, you'll notice that this matrix using reshape to 3 by 2 is not the transpose of the first matrix. If I look at the first matrix and wanted to do the transpose of it, it would be rows of 1, 2, and then 3, 4, and then 5, 6. But that's not what we've got here. It's just taken the elements of B in the order in which they occur and reshaped it into 3 rows and 2 columns, all right? So that's your reshape function. And then I will mention, let me go to the slide to emphasize that. I will mention that what is essentially happening here is it's flattening the first array and then reshaping it into the final product array, all right? A little bit tricky, but I think the example gives you an idea how that works. There's another method that I don't illustrate here that is called resize, and it changes the view of the array, but it is still the original array, and that's similar to the Ravel method, okay? So, we're going to move on now a little bit and talk about indexing arrays and review that. So let us get rid of a few of these because we don't need them. And we'll start with a new one here. Get rid of the comments and put in our usual loading of the NumPy module. And then we'll create a couple of arrays here that we can do some examples of indexing with. All right. So first one is just going to be one-dimensional. One 1.2, 3.5, 7.9, 8.4, and 9.9. Okay, so there is our one-dimensional array, and then we'll have a two-dimensional array that we can work with also. Two brackets, and it'll be the one we used before. 1, 3, 5, and 2, 4, 6. Okay, so we've got those two. So now what I'm going to illustrate here is, just so we're reviewing this, is I'm going to print A index 2. All right, I'm going to print that, and we see that that's 7.9. And you will notice the 7.9 is the third element, because the array indices are zero-based. So the first element is index 0, second one is index 1, third one is index 2. All right, and then we'll try another one here, print B, and it's two-dimensional, so we'll put 1, 2. Sorry. And let's print that. And you'll see that we get 6. All right. Now remember that in terms of rows and columns, 1 would be the second row and 2 would be the third column. So as we look at B over here, second row, third column is 6. All right. So you have to be careful with the zero-based indexing. And then the final thing we'll illustrate here is using the colon operator. And so let's come up here and let's try So let's see what we've got there with B, with 3, 4, with getting 3, 4. Well, what the colon means is all rows. So that means we get both the first and the second row. And the 1 means the second column. So that shows you how we get 3, 4 there using that colon operator. And then the other one we'll try is our lowercase a, and we will use an index of 1, 3. All right. And we'll see what we get when we run this. And it's 3.5 and 7.9. Now here's where it's a little tricky with the colon operator, typical Python-like thing. And that is that we'd start at 1, which is the second element of A, which is 3.5. And then colon 3 would sort of indicate to go to the fourth item, 8.4. But when you use the colon operator, as we've seen before, and we saw it with range type and with the arange function, is that you don't get the last item indicated. So this would be item 2, and then 3, but not item 4. So it just gives you 3.5 and 7.9. All right, so let's go back and review that. First, we show here on the slide how we've got typical mathematical subscripts for an array or matrix, row column, row 2 column 3, and what the indices would be for that in Python. So row 2 column 3 would be index 1 comma 2. All right, that's just shown in laid out for you. And then here are the examples that we used and what the results were and the explanation provided. And also, when we actually display this one of colon comma 1, it is displayed as a row, and it's as a one-dimensional array, as it were, and not as a multi-axis or multi-dimensional array. All right. So there you've got that, and now we want to just make sure that you understand how to handle this colon operator when we have a multi-dimensional array with a few more elements to it. So let's come back over, and I'm going to pick up a file which is called indexing examples 2. And what we've done here is we've created a 4 by 4 integer array, and then we have printed 1 colon 3, 1 colon 3. So let's see what happens here. There are results. It gives me -1, 6, -8, 4, and you can see that right here in the middle. And the way that this is working in each case, the first item here, index 1, means start with row 2 and start with column 2. That's the -1. And then when you see the 3, it says don't include 3, but go up to 1 before it, which would be 2, and here 2. Okay, so this would say go up to row 2, go up to row 3, and then over to column 3, which would correspond to the indices for 2 here, all right? And don't include the 3, which would imply going to the 4th row and the 4th column. So that gives you an idea of how to handle that. And then one thing that turns out to be sort of a convenient coincidence is what happens when we index or look at array elements using for loops with the range type. So let me bring in an example to illustrate that. It's called indexing examples 3, excuse me. And so what we've done here is we have set up a 2-dimensional array, 1, 3, 5, 2, 4, 6, which we've had before. And then we're doing some calculations here with a pair of nested for loops. And you'll notice that essentially the dimensions of our array are 2 rows, 3 columns. So we say for I in range 2. Now, if you'll recall, what that means is it produces a list of 0 and 1, which then correspond to the appropriate indices for the array. And then we say for J in range 3, which produces a list of 0, 1, 2, which corresponds to the column indices 0, 1, and 2. So we can use range with the actual count of row and column dimensions, and then use that here in index in the loops, I comma j, and it will turn out to give us the appropriate reference. And all we're doing here is we're summing up the square roots of these elements. So when we run this, we get an answer of 10.83, and this shows our original matrix up there. So that we'll see that over and over again, where when we use the range type, we're able to put in the actual size of each axis of the array, and then range will give us a list of the appropriate zero-based indices. Okay? So let us come back and review that with our slides. These are the two examples that we showed you where when we put in 1 to 3, it gives us rows 2 and 3 and columns 2 and 3, all right? Which are indices 1 and 2 correspondingly, indices 1 and 2. And I apologize for the confusion between these business of rows and columns and actual array indices. That confusion does not arise in MATLAB, but you have to learn to live with it in Python. And then down below, it shows the example that we did with the nested for loops using 2 and 3. Okay, so let's move on now, and we're going to illustrate some operations that you can make with arrays. So let me close out a couple of these and open a blank one. We'll type in a couple of examples here. And we'll create a one-dimensional array from a list 1.2, comma 3.5, done this before, 7.9, 8.4, and 9.9. Okay, we create that, and then as an example, we take another array and we divide the A array by 3, and then we can, for instance, print B. So when we do that, what we notice is that this is an array operation. So the divide by 3 divides each element of our array A by 3. And so we can do operations like this on an array, and it does it item by item, what we would normally call an array operation, all right? And then, you know, a second example that we could do would be do an A again differently, NP A array, and put in a list of 1, 3, 5 of integers, and B, NP array, and then in brackets 2, 4, 6, and then we could say print A plus B. And when we run that one, what you'll notice is it gives us 3, 7, and 11 down here, which you can see by adding the elements. So we can do addition and subtraction in arrays, but they have to be conform to the same size. And that is what we would expect in terms of matrix and vector operations, and for instance, in using MATLAB, all right? And then the final one I will do is showing you how we can, because we're dealing with arrays, we can do array operations with more complicated formulas. So we'll create an array X equal to 0.1, 0.2, 0.3, and then we'll have a formula Y is equal to X cubed minus 2 times x squared plus 0.4 times x plus 3, a cubic equation or formula, and then we can print y, all right? And if we do that, we get the evaluation of the polynomial for x equal to 0.1, 0.2, and 0.3, right? And so this, you've seen us use this before, where we take advantage of array operations, this is the kind of thing where if you tried to do this in MATLAB, you'd get into trouble because it would want to do a matrix operation and not an array operation. So you end up using the dot operator before something like the exponentiation, which is a caret character in MATLAB. So there you have 3 examples of array operations in Python using that, and those are illustrated. And sometimes they call this latter operation a vectorizing operation, but the idea is that x is an array and it's put through this transformation and it produces a similar sized array of answers. Okay, and this is available in a separate file which I did not load. Okay. And I want to point out a distinction that we've mentioned before. So let us come back over. And I'm just going to add on to this particular code. I'm going to say import the math module. And then I will say print math.assign, S-I-N, sign of x. And I will try to run that. And it doesn't like it because the functions in the math module do not accommodate array operations. They only can be used with a single argument and not an array argument. However, if I get rid of the import math and instead precede that by NP sign, then it's perfectly happy because the NumPy math functions support array inputs. Okay? So I think we have a slide that reviews those two, shows you the error that you get when you try to use the math module, so don't do it. Quite often we generally use the NumPy functions, and we don't use the math functions just because they work for both single and array inputs. Okay? All right, so I want to show you a contrast between an item-by-item calculation and a vectorized calculation, which indicates why we generally take advantage of vectorized calculations. So let's come back over here and start a new script. And I'm just going to create an array using the linspace function. We've used that before. And I'll say we're going to go from 0 to 10, and we're going to have 25 equally spaced points. And then the length of this array, we can calculate and assign to n. You'll notice that the len function is a Python function and not a NumPy function. And then what I can say is that what I would like to do is create a y array which contains the hyperbolic cosine of all the x values. So one way I can do that is I can say y is equal to np dot zeros of n. In other words, I can create an empty array or an array of zeros that is the same size as my array of X. And then I can go for I in range N. And that's going to give a list from 0 up to n minus 1 for indexing purposes. Then I can say yi is equal to np dot hyperbolic cosine, COSH, of x index I. Notice the indices are in brackets, and that will compute my values of y. All right? We can hope. So if I run that, here are my x values, all right, from 0 up to 10, and my y values for each one of these, all right, is computed. So we can do that. It's a little bit long-winded, but if we take advantage of array operations or vectorized operations, it's much simpler to just come in and make the calculation with one statement, because we're putting x as an array into this calculation and it produces y as a similar sized array. And I'm hoping this gives the same result, and it does. Okay? So that we see, you see that also in MATLAB, where you've got an item by item calculation using a for loop, and you can make that much simpler by just using a vectorized or an array operation supported by the NumPy package. Okay? So what we're going to do now is we're going to take a look at a couple of the standard operations that are matrix based. And the first one of these is going to be matrix multiplication. Sorry about this. So let's come back. And this slide, I think you're pretty well familiar with what matrix multiplication is, but this lays out the multiplication of an M by N matrix A with an N by P matrix B, yielding an M by P matrix C, and it gives the shows how it happens and gives the necessary calculations here. So we can actually set up the code for doing that. I'm not going to type it in because it's a little bit longer, but let us remove a little bit of this. We don't need it anymore. And I'm going to open a file called matmult example. Went by it. There it is. Okay, and so this has some interesting features to this first part of the code here that are new. And that is, it's a function called matmult that we can call, all right, with array A and B. And you know for matrix multiplication that the number of rows in A have to be equal to the number of columns in B. So what we do here is we don't know the size of these arrays since it's a function. So we find out the number of rows and columns in each array using the shape method from Python. That's something you haven't seen before, but it's a useful method. And so we use it and we come up with those. And then we have to make sure that the number here and the number of here are equal. And so if they are not equal, we have to essentially get out of the function and we just return an error message. Otherwise, we go on and we create an empty C matrix and actually go into 3 nested for loops in order to compute the product, all right? And so that is the way we do that in terms of a function, and I've set up a matrix here, A and B, all right, where A has 3 rows, 2 columns, and B has 2 rows, 3 columns. And I do the matmult function to get the answer. And then, just to show how we get around all this, I show that we can use the dot method in Python, not associated with NumPy, in order to carry out the dot product of 2 multidimensional matrices or arrays, which is the same as matrix multiplication. So we can do A dot dot of B, and if we do that, we get the same answer for each of them, all right? So that's what that looks like. So the important thing to note down here is that when you want to do matrix multiplication, is that you can do it this way. And it's not as simple as you can do it with MATLAB, where you just use the multiply operator. But if you got a reference to how to do it here, then you know what to do when you need to multiply 2 matrices or 2 vectors, or matrix times vector, or vice versa. Okay, so let's come back over, and this shows the matmult function, and it shows this shape. And it shows this shape method that I used, which is I'm introducing as new, and then it shows the results. 3 by 2 times a 2 by 3 yields a 3 by 3, and then we can do the dot method and we get the same result. But we prefer this because we don't need to carry that code around with us for matrix multiplication. Okay? And to finish up here, we've just got a couple of other operations. One is the transpose operation, and the other is the matrix inverse. So let us come back over to our editor. And illustrate transpose, which is very simple. We'll create a 2-dimensional array here. -2, 5. Second row is 7, -0.5. Third row is -4 and 3.4. Okay, it seems to be happy with that. And then we use, again, a method inherent to Python for arrays, which is a.transpose with no arguments, yielding B. And then we can print A, followed by a blank line, and print B. See how this goes. So you recall we did a reshape, and I mentioned that that was not equivalent to a transpose, and this, of course, is a transpose. So here, as we look at it, the rows of A become the columns of B, and that's how you can carry out that operation, okay? And this code is available in a file, although it's very simple. And if we look at the slide, that indicates how we went about doing that, all right? So you can see with some of these operations, like the dot method and the transpose, we can use methods inherent to Python. Now, there may be an alternate dot product method within NumPy. I'm not taking the time to give you all these details now because what I'm showing you works perfectly well, and we'll be using it as we go along. And the final example that we're going to show you is the matrix inverse, all right? And I'm going to load in some code to illustrate that because it will take a little bit longer to type in. And so this is matrix inverse example. And here we are doing our normal import of the NumPy module, but then we're also importing a sub-module of NumPy, which is called LinAlg, stands for linear algebra, right? So we're bringing in some additional features that are available to us. And so what we do in this first block of code is we just create a 4x4 matrix, and we're using a particular matrix here called the Hilbert matrix. And so we calculate the elements of the matrix as 1 over I plus j plus 1. And again, we use the range type here. The size of the matrix is n by n, and then the appropriate indexing takes place with going from 0 to n minus 1. That gives us A, and then what we say is we want the inverse matrix, and we could actually program fairly lengthy code to compute the inverse, but in the LinAlg module, we have an INV function that will do it for us, all right? And it'd be similar to what we have in MATLAB, and also a similar function available to us in Excel with VBA. And then when we're done, what we're doing here is, you know, when you multiply the inverse by the original matrix, you're supposed to get the identity matrix. So we do A dot with AI and print that out to see what kind of result that we receive. All right, so let's run this. And coming back up, this is the original Hilbert matrix that we calculate by the internal formulas here, all right? So the last one here is the 4,4 element, or by indexing the 3,3 element. So we would have 3 plus 1, which would be 1/7 here, and it would work its way back up to 1 in the upper left-hand corner. It turns out that this matrix is what is called ill-conditioned, and it's fairly difficult to compute the inverse. And so this is the inverse matrix that we get using the INV function. And you'll notice that the numbers are sort of getting big here compared to the smallest number, and that gets worse the bigger this matrix becomes. And then finally, the multiplication of the two shows that we have ones on the diagonal and either zeros or something close to 0 on the off-diagonal elements, which means that we're dealing with a numerical procedure and we're dealing with numeric precision, and it doesn't give us precisely an identity matrix, but something that is virtually the same as an identity matrix. So our last slide here shows us the code for this and the results, and makes the comment that the result is numerically very close to the ideal identity matrix. So that's how you do a matrix inverse. You've seen how to do a matrix transpose, and then a matrix multiplication. We also have shown you that you can carry out like matrix operations by a scalar, multiply or divide very easily as an array operation. And also you can use the addition, subtraction, and as an array operation, and it's very easy to do that. So those are the array and matrix operations that we wanted to review, and that brings us to the end of this first workshop. I want to make reference here to a book that I have written, collaboration with my best friend and co-author Steve Chapra from Tufts University, that is essentially a Python book for use, covering all of these topics, and it has come out just this past year. And then I have an inspirational cartoon for you, and I'm going to say where we are headed now, and that is to go on to the second workshop in the Python Bootcamp series, where we're going to be using all these tools to solve some typical problems that we encounter as chemical engineers. So thank you for hanging in there, and we'll see you in the next workshop.